Okay, functions and data analysis fans, our topic for today, this is section 2-4, permutations and combinations. Before we start, let me tell you your joke of the day. I had a dream last night that I was a muffler. I woke up exhausted. All right, so in section 1 here, we're going to look at what's the difference between what we call a permutation and what we call a combination. So we're going to look at example number 1 to kind of sort this out. How many ways can you choose, this is part A, how many ways can you choose 2 letters in the set, and we have 4 letters, A, B, C, D, if repetition is not allowed? List each arrangement. So we're only choosing 2 letters out of those, and repetition is not allowed. So we could go A and B, we could go A and C, we could go A and D. So if we start with A, we could also go, so you can't do AA because they say you're not allowed to repeat. We could also go B and A, B and C, B and D. You can't do BB because you're repeating. We could go CA, CB, CD, and we could go DA, DB, and DC. Okay, now normally we're not going to write down all of the ways of doing it because we have an easier way to count this. To choose the first letter, we have 4 choices. We could go A, B, C, or D. So we pick one of those. So for the second letter, since you're not allowed to repeat it, there are only 3 choices left. So 4 times 3 is equal to 12. And this is what we were doing the last day, the last lesson. Now part B asks though, what if the order does not matter? What if AB is actually considered the same as BA? So in other words, if we have AB and BA, those are being double counted. They should only count once. Now if we list the possibilities, well, AB, AC, AD. Now we can't go back to BA because that's the same thing, and we don't want to double count. So we could do BC and BD, and then we could do CD, and that's it. We can't do CA because we already have it. We can't do CB because we already have it. So now if the order does not matter, now we only have 6 ways of doing this. The way we can get that, well, we can do 4 times 3 again, except now that we're taking out the part that repeats, and we're saying that AB and BA are the same thing, we can divide by 2 factorial. And what we get is 12 over 2, which is 6. Right, so if the order matters, it's different than if the order does not matter. If A, B, and BA are different combinations, or I'm sorry, different arrangements, then we say the order matters. So in part A, order matters. And that is what we call a permutation. If the order matters, that is a permutation. However, if the order does not matter, so order does not matter, that is called a combination. So one of the questions that we're going to ask ourselves when we look at the problems, does order matter? Now another way you might hear this, order matters or is significant. It's important. Order does not matter, it is not significant or not important. Okay, so let's look at another example. Let's do number 2. In a group of 10 people, so this is part A, you choose a president, a vice president, and a treasurer. How many ways can you do this? Well, we are assuming that the president, the vice president, and the treasurer, these are different positions. They have different responsibilities. So for this, since these are all different, we would say that order matters. It would be different if you are the president or if you are the treasurer. Those are 2 different situations. So we have 10 people. We're going to choose the president, the vice president, and the treasurer. We have 10 ways to choose the president. Now, whoever's president can't be two different things. So then there are 9 people left to choose vice president and 8 people left to choose the treasurer. And the counting principle says that we multiply that and we get 720 people. 720 ways to pick 3 of those people. Okay, now let's change the problem slightly. In a group of 10 people, again, you select 3 people for a committee. Order does not matter. So if you're on a committee, it doesn't make a difference if you're chosen first, second, or third, because it's all the same position. It's the same power for each position. How many ways can you do this? Well, 10 times 9 times 8, but we have to divide out the number of ways of arranging 3 people, which is 3 factorial. And so we get 720, but then we have to divide by 3 factorial is 3 times 2 times 1, which is 6, and that's 120. So if the order does not matter, you're going to have less ways of doing something because you have to take out the parts that are repeating. So order matters, that is a permutation. Order does not matter, this is called a combination. Now, doing both of these parts, we kind of thought our way through the problem, but there's a formula for figuring out a permutation or a combination. So NPR is the way that we write a permutation. NCR, the C is for combination. So P is permutation and C is combination. So here's the formula. NPR, the way we read this, N is the total number of objects. So N is the number of objects. R is the number of things we choose, is the number that we choose. So N is the number of objects you have. So it could be people, 10 people, and then we're going to choose 3 of them. That's what was happening in problem number 2, part A. And the way that we'll read this is N permutation of N objects taken or chosen, taken / chosen, R at a time. R at a time. Okay, and I'll explain that in a second here. But the way that you calculate it is you do N factorial divided by N minus R in parentheses factorial. So for example, if we do 10p3, which was basically number 2, part A. We did a permutation of 10 objects and we chose 3 of them. So 10p3, 10 objects taken 3 at a time, it would be 10 factorial over 10 minus 3, so n minus r factorial. Now that's 10 factorial divided by 7 factorial. And what's going to happen there is we get 720. Now, if you're trying to simplify that, how does that end up being 720? Well, 10 factorial is 10 times 9 times 8 times 7 all the way down to 1. Now, I'm not going to write 7, 6, 5, 4, 3, 2, 1 because I can just write it as 7 factorial right there, divided by 7 factorial. Now we can divide these out because they are the same. 7 factorial divided by itself is 1, and what we get is 10 times 9 times 8, which is exactly what we wrote down here. So we have been doing permutations without even realizing it, and this is the way that you can think through the problem, and this is the way that you can solve it with the formula. Now with a combination, the formula is NCR, so the number of objects taken R at a time. Again, it's n factorial on top, but notice that in the denominator, we have the n minus r factorial, but we also have r factorial. So what happens if we do a combination of 10 objects and we choose 3, it would be 10 factorial over Now the r value is 3, so r factorial would be 3 factorial times 10 minus 3 factorial. Now we can simplify. That's 10 factorial over 3 factorial times 7 factorial. So really, it's the same setup as the permutation, but then we're also dividing by 3 factorial. And if we decide to type this, so we can do 10, let's see, factorials, we go math, and we go over to PRB, probability, and down to number 4, divided by, now I'm going to type it, I'm going to say 3 factorial, and then 7 factorial. Now the way that I'm typing it with the slash here for division, I have to put this in parentheses because I'm dividing by this whole thing. And what we get is 120 for that. And that was the answer that we got in number 2, part B. Okay, 120. So this is 120. Now to be honest with you, there's a faster way of doing this. You can actually do this with the calculator. You can type this in. Let me show you this. If we go, I'm going to type 10. Now, if I hit the math button right there, and we go over to, so you can see this, PRB, notice that number 2 says NPR. Well, I'm going to select that. So 10, permutation, and I'm going to type 3. We're going to choose 3 of them, and that gives us 720. Now, if I want to do the combination, I can go 10, and then math, over to probability. Now, combination is NCR, so 10 objects chosen 3 at a time, and there's your 120. So you can actually calculate these pretty fast. So let's do the last problem at the bottom here. Number 3, evaluate the following. So A is a permutation of 9 objects taken 3 at a time. Now if we want to set up the formula, it would be 9 factorial, that's the n factorial, over 9 minus 3 factorial, and then we can work that out. But honestly, the way I'm going to do it here is I'm going to type 9 math NPR and 3 and hit enter, and we get 504. And then for part B, which is 9C3, is 84. So we get 504 for part A, and then we get 84 for part B. I'm not as concerned with us doing the calculation, of more understanding when would it be permutation, when would it be combination, and that's what we're going to look at on the back. Now let's do these last 2 here. So a permutation, 24 objects, we're going to choose 21 of them. So 24 math, NPR for permutation. Now we're going to choose 21. That's a lot of choices. And it's 1.03 times 10 to the 23rd. 1.03, all of this. E23 means times 10 to the 23rd. So let me write this down, 1.03, this is scientific notation, times 10 to the 23rd. What that means is that after this decimal place, we should be shifting this 23 places to the right. So it should be going way out to here, and with all the empty spaces, you're going to have a bunch of zeros. So this is a huge, huge number. Now, if we change that to a combination, notice that it's not as big. I mean, it's not even close. It's 2024, and that's going to be your solution. So again, a permutation where the order matters, you can get very, very large numbers. For a combination, though, it's always going to be less because you have to divide out the parts that are repeating, that are basically saying the same thing. That's the end of part 1. Go ahead and flip it over, and we will do some examples on part 2.